All right. So, real quick before we get back into the math, great job on the exam, everyone. I said a bunch of good stuff in the email, right? Overall, everybody did great. I was extremely pleased. Grades accordingly. So it's an everybody wins situation. Okay, so here's where we were last time. We were talking about line integrals and how to compute line integrals and, computing with parameterizations, and we made the observation that the parameterization doesn't matter, but there's a pretty big asterisk on this. You're not parameterizing a, what I like to call a dumb curve. You're parameterizing, where did I put my picture? Here it is. You're parameterizing an oriented curve, and the orientation is part of the deal. And so your parameterization has to be consistent with that orientation. So you gotta parameterize in the correct direction. Or said differently, if you don't parameterize in the correct direction, you're not gonna get the right answer. Okay. However, as we saw last time, you will not get the right answer in a very predictable way, right? You will be not right by exactly a factor of -1. And so that's what we have here in this theorem. Keep in mind, this superscript minus sign is a convenient notation to just say, look, it's the oriented curve, kind of like C, but going the opposite direction. And we have this nice theorem that says, yeah, when you go the wrong direction, you will get the negative of what you should have got, right? So this can be used in a couple of nice ways. All right, so we're going to go on with an example here. Let's see here. Why don't I go full screen? This example, I'm going to show you 4 different ways to answer this question. I'm not going to go through all the details of all of them. I'm just going to show you kind of what's new about all of them. 3 of the 4 are acceptable. One is not. We'll do that one last. And of the 3 that are acceptable, one of them is very clearly much better than the other 2. Okay, so anyway, here we go. Let's start with the acceptable but not really the best way to do it moves. Suppose you're walking counterclockwise on the top half of the unit circle. So this is the same situation that we had with the previous, the last example we did yesterday. But this time we're going clockwise. So we're going like this. Okay. So the first 2 different solutions I want to show you are basically 2 different ways to create a parameterization of this oriented curve going clockwise on this top half of the unit circle. So the first observation to make is that you can make this happen just by, this point doing what it's supposed to be doing. You can achieve by defining t to be that angle. And then notice when t is 0, you're at the far left point, and then as t increases, you move in the correct direction and end on the far right. Can I do sines and cosines using that angle and, invoke polar coordinates and stuff like that? Well, no, I can't, because that's not theta. However, theta, pretty easy to note, is just pi minus that. And if you are looking to parameterize a point, if you want to write down the formula for the coordinates of a point where you know the literal polar angle theta, then hey, sines and cosines. Well, let me do it like this: sines and cosines. Right? Cosine theta, sine theta. That's how that works. No problem. And now, what does that have to do with writing this all in terms of t in the most convenient way? Well, you have to know your angle addition formulas. And that's just, old trig right from way back. And my recent experience has been that somewhere along the way, high schools just decided that y'all don't need to know that. I think they're extremely wrong. I think all students who are going to go into engineering, for example, the angle addition formulas are going to come up. They're certainly going to come up in this class. So, FYI, I am going to assume, let's say that differently, you are expected and required in this class to know the angle addition formulas for sine and cosine. They're in any trig textbook. I'm sure they're all over the internet. So anyway, make sure you know just sine and cosine, just those 2. but you do need to know those formulas. Okay. All right, so that's one way to do it. Now, here's a different way to parameterize. Now, again, we're interested in parameterizing this path where we're walking clockwise. And I'm going to make the observation that I already know how to parameterize this path going counterclockwise because it's our old friend. It's one of our very first parameterizations. So that green parameterization is easy. And then the clever observation to make is that these are clearly reflections of each other over the y-axis. And so if you want to know the formula for the blue position as a function of time, and you know the formula for the green position as a function of time, yeah, just reflect. And not hard to persuade yourself that when you reflect over that, what that reflection does is it puts a minus sign on the x-coordinate. So anyway, now why am I showing you two different ways to do the same thing? Well, it's a tools for your toolbox kind of a situation, right? There will be some situations where this reflection argument will solve your problem, but this sort of angle argument or something like it just kind of, for whatever reason, just won't work. Right? And vice versa. So I think it's good to have tools at your disposal. These are two good tools to have in mind. And then whichever of these tools you use, of course, once you have your parameterization, then plug and chug. And y'all can totally do that. Okay. That's two solutions. Number 3, the best one, uses this theorem. This theorem says, look, if you go the opposite direction, just throw a minus sign on there and you're good. We've already gone the wrong direction. We've already computed the amount of work it takes, wrong color, the amount of work that it takes to go counterclockwise. We already know that counterclockwise work is pi. Well, okay. Then here's the breakdown. The work that we want to compute, well, that is just, this path that we're interested in is literally the green path, the opposite orientation path, backwards. And we already know that going backwards gives you a minus sign, and we already know that going counterclockwise gave us pi. Minus sign. Red. Boom. Done. Right? Way better. Right? So there is a case to be made that, parameterizing the wrong way on purpose, as long as you apologize appropriately by putting the appropriate minus sign on there, is a perfectly respectable way to compute a line integral. Right? And I encourage that, even if there's, for whatever reason, if there's some advantages. And in this case, of course, it was massively lucky because we had literally already done the counterclockwise computation. But even if we hadn't, wrong way, rather than thinking through the whatever version of how do I parameterize this backwards, probably more trouble than just saying, let me write down the parameterization I already know, and minus sign, boom, fixed it. Right? Writing a minus sign is probably easier than figuring out how to parameterize backwards. So, highly respectable, perfectly decent way to do it. Probably my favorite of the 3. Okay, the 4th solution, air quotes, solution. I don't like this at all. In fact, keeping in mind, I know y'all heard me say it a million times, you're probably going to hear another million more. Doesn't matter if you get the right answer. The answer is not what this course is about. This course is about valid mathematical reasoning, clearly communicated, right? That's what we're doing here. Some students like to make what I call the time travel argument, right? And say, I'm going the opposite direction along this existing, green parameterization, the cosine comma sine parameterization. And if you want to go the opposite direction, well, then instead of going from, 0 to pi, you're going from pi to 0, and they just switch the bounds. Okay, well, here's the thing. I mean, yes, that will get you to the right answer because, well, in fact, switching the bounds does introduce a minus sign, and as we just discussed, the minus sign is, what you need to get to the right answer. But again, doesn't matter. The answer is not the thing. The argument is the thing. Okay, so what do we make of this? What's the argument underneath all of this? And the argument is full of problems. Right? For one thing, I don't think I can make any reasonable case that I understand time travel. Right? And I'm not really going to buy it if you claim to have an understanding of time travel. Right? So there's that little matter. But the other thing is, when you do something like this, if you just say, well, we're going to have t going the other way, certain things that we take for granted aren't true anymore. Right? So if you're saying, look, I'm going to use the usual framework of parametrizing and taking a derivative and arguments about tangent vectors and distances and blah, blah, blah. You're going to use all that framework that we created for how to compute these integrals. But you use it in a way that makes parts of that framework not true anymore. Then you're not using the framework. Right? And so there's a lot of nasty questions as to, wait a second, well, do the part that I'm actually doing, does any of that get affected by, what I've done here breaks some parts of the story, but it doesn't break other parts of the story? You've got a lot of problems to deal with. Right? So the main point I want to make here is, what's to be gained? Right? What does this buy you? Right? Where did I write this? No compelling advantage, right? This does not buy you I don't think it buys you anything over just opposite orientation means a minus sign, right? How is this somehow easier than that? It's not. Right? So there's no compelling advantage to this. And the disadvantage is it makes your argument extremely unclear as to what did you mean and did you think it all through. Because, well, probably didn't. So for the purposes of this class, I'm going to say I think that's, I'm going to basically disallow it. It doesn't really, there's a lot of problems there. Yes?
So essentially when we're computing line integrals, we should not do it with respect to dt.
No, you'll absolutely do it with dt. And so, for example, if you look at when we did this one here, right, that in the dot 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 is dr is r prime dt and all of that. But the point is, we're applying that to a parameterization that is going the direction it's supposed to be going. And so, yeah, absolutely, yeah. But my problem is if people do this move, where they have the bounds in the wrong order. Because it's just, it is not the simple treatment of the scenario at hand that a lot of people think it is. Right? Is everybody happy with that? Yeah.
I mean, I'm sorry, if by any chance you could show us an example of where
sure.
we may use it and then...
You may not use this.
No, where we may accidentally end up using it.
Well, in this exact problem up here, right? So, we want to take the same curve that we did yesterday at the end of class, where you want to go clockwise instead of counterclockwise, and there is a point of view that says, well, this is my parameterization, cosine and sine, and well, I want to start here. Go clockwise. Here is where t is pi, and I want to go over to here where t is 0, and so students will write down pi to 0 like this. And I'm just pointing out that is fraud, right? Because again, there's nasty little situations. Like, for example, if this is literally your parameterization, then the derivative is, I can't write. The derivative is that way. That's what r prime is. That's the derivative. But the velocity vector, you are literally going that way. So these are no longer equal. And oh my gosh, what else has gone wrong? Oh no, right? The big problems. Is that satisfying?
Yeah.
Okay. Yeah. Yeah. Good. Okay. All right. So moving along, we've got this thing called a vector line integral. This thing called a vector line integral, we know that it represents work, but hey, whoa, slow down. Specifically when the vector field is a force that you are applying as you move. If the field is a force, then the line integral represents work. Okay. Yeah, right. Okay, but what if the force, whoops, that wasn't the color I wanted. What if the field represents a fluid flow? That's one of our other metaphors for vector fields. It's a very common and useful scenario to think about where a vector field could be useful. Okay, well, if our vector field represents fluid flows, notice no more forces. No forces in the discussion at all. Then what does the line integral represent, right? It can't be work because there's no forces. So this has got to represent something. It isn't work. What is it?
Displacement.
There was a rhetorical question. Sorry. It turns out that it's a hard thing to talk about. So that's the question that we're going to consider. And here's the short version of the answer is that in this scenario, when the field represents a fluid flow, vector line integrals represent the answer to a weird question. Right? So what I'm going to do is I'm going to start by asking and then answering that weird question, and then we'll make the interpretation after the fact. So here's the weird question. Suppose you have a curve, as we've drawn here, and suppose you consider this thin region around your curve. You'll note as defined by some cross-sectional area. So imagine that you take your curve and you kind of drag this area along the curve, where the area remains perpendicular to the curve. So you just kind of drag that along, and that makes this kind of long, thin, kind of tube-like thing, right? And with that region defined, here's the question we want to ask. It's a weird question. I want to look at every little piece of fluid, right? Every little piece of fluid in here. And looking at each piece individually and then adding up over the whole. I want to know what is the total rate that those little pieces of fluid all together, what's the total rate that they're moving specifically along the curve. And it's a weird question to ask, and one thing that pretty common little guide that we try to follow when we're doing math is we answer questions that we know why we're asking. Right? I mean, asking some random weirdo question, why are we doing this? Right? So I am asking y'all to trust me for a moment. It's going to turn out to be very relevant. So first of all, let's answer the question, though, and it's just a matter of kind of writing some things down. Notice that each little piece of fluid has a certain amount of volume of that fluid. And for each such piece of fluid, I can talk about the field vector, but I'm not interested in the actual velocity of the fluid. I'm interested in the extent to which that fluid is moving along the curve. So therefore, I'm interested in the t component, right? The tangential component of the vector field. And so for that one little piece of fluid, this product is in some sense answering fluid R moving along the curve, but just for that one piece of fluid. So then adding up, let's see color choices. Adding that up over all of the entire fluid, we get by just integrating. Say we're going to add that up over, all along the entire curve. So now a lot of this y'all know how to do. Y'all know how to compute components. Right? T is a unit vector, so component is a dot product. And volume is area times length. Right? Pretty straightforward stuff. And when you throw the integral in there, you end up with, this expression. Right there. Right? So the answer, this total rate Q, there it is. It's the area times the line integral. How about that? The line integral that we're interested in has showed up as part of the answer to this question. So with that in mind, I'm going to rephrase the question. I'm going to say, let's look at this little piece of area here. Let's divide that over to here. Right? We're going to change the question then to, it's combined extent that the fluid is flowing along the curve per unit area. Divided by area means per unit area. And let's just point out, the bigger the area is, more area, more fluid, more Q. Right? So of course it should be proportional to the area. That's pretty plausible. More area means more fluid, means more Q. So it becomes then arguably a more natural question. And that rephrased, we have then the answer to what we're looking for. What is a line integral? A vector line integral is the extent to which the fluid's moving along the curve. Per unit area, of course. Obviously, more area, more stuff, right? So, very nice and crisp little answer there. The line integral represents in some sense, the combined extent to which the fluid is flowing along the curve. And there you go. Yeah?
Shouldn't we have units of volume per unit time?
We do. Because area times, now you got to keep in mind that dr has units of length per unit time because it's a velocity. Well, it's r prime dt, right? So r prime is a velocity and dt is a scalar. So so it works out. It's volume. Gosh, let's think about it. It's volume, but the extent to which it's moving along the curve is length per unit time. So it's volume times length per unit time, and the vector field has units of the vector field represents velocity, so that is length per unit time, and dr has units of length. So it all checks out. Yeah. Right. Okay, so this is the interpretation. Here is just a couple of pictures just to kind of, get some geometric intuition. So now I'm going to show you a special case here. Specifically, we're going to look at something called a closed curve. Right? So a closed curve starts and then ends at the same point. That's what a closed curve is. In this special case where we're talking about closed curves, for the case of a closed curve, the line integral, we have a special term for the line integral. The line integral is called a circulation. If you think about it, the line integral represents the extent to which the fluid's flowing along the curve, but the fluid flowing along a closed curve that kind of circles back to where it started, you're measuring the extent to which the fluid is kind of going around like the curve is. So I think that term circulation is pretty reasonable. How y'all, is that cool? Is everybody all right with that? Okay, so let's play the game. Let's think it through. And we'll look at this scenario first where on the left where our curve is like this. So there's a curve. And let's think about the line integral. How would I understand the line integral here? Well, the line integral supposed to be measuring the extent to which the field is flowing along the curve. And, well, now just use your geometric intuition. this fluid does appear to be literally flowing along the curve. So I feel like in this situation, to what extent is the fluid flowing along the curve? Well, quite a bit. And if you were to, quantify this, parameterize such a curve and create such a vector field and compute that line integral, indeed, you would get a positive value. Everybody see what I'm talking about? This is what we mean when we say fluid flowing along the curve. Okay. All right, now let's look at the next example. Next example here. Here's our curve. Notice it looks an awful lot like the original. It's going the other way. Oh, yeah, question.
Sorry. The curve is F, yes?
The curve is C.
Okay. C,
Yeah.
and then F would be the
F is the vector field.
Yeah, the vector field around
Yep,
it. Okay.
yep. No worries. Yep. Okay, so next one, here's the curve. Pretty much the same underlying curve, but just oriented in the other direction. Okay. All right, but and of course we know when you orient the other direction, that's a minus sign, so in some sense we know where this is going to land. But let's think about it from the point of view of the intuition that we're pushing. To what extent is this same fluid flowing along this blue curve? And here's the tricky bit. It's kind of flowing along, but it's flowing opposite. I mean, it's parallel to the curve, but in the opposite direction. The curve's going that way, the fluid's going the other way. So to what extent is the fluid flowing along the curve? The curve being clockwise, the fluid flowing counterclockwise, it's opposite. Right? So this should count as negative flow along the curve because it's going backwards. And so you should guess that if you were to compute this entire circulation, you should guess that it would be negative. And again, if you quantify everything in the picture there, it will be negative, yes.
So the circulation value that you get is from computing the line integral with the curve?
Yes, that is exactly right. So this line integral is called circulation. Yeah, so literally line integral is circulation. Absolutely. For a closed curve. Yeah. Okay, so that's sort of what the picture looks like, and very often, such as in cases like these, you can very often just kind of eyeball glance, and you can just look and see, is the fluid flowing along the curve? Is it not flowing along the curve? Is it flowing backwards? Very often you can eyeball glance. Just for the record though, sometimes it's really not obvious. Right, you take this curve here, for example, and it's like, well, in some places the fluid is flowing backwards along the curve. In some places it's flowing forward along the curve. You're going to have a tug of war of pluses and minuses here, and we're going to have to do some speculating in a case like this. It's not immediately obvious. And it turns out we're going to develop, possibly today, some sophisticated tools that will allow us to take a nicer view on stuff like this. A very cool idea, either today or tomorrow. Yeah?
Could the circulation be the integral of the curls at every point?
You're getting ahead of me.
Okay.
I like where your head's at, but let's. I want the ideas to reveal themselves for both dramatic purposes and also for sort of intellectual development purposes. I want to be able to give you some sense of justification. Yeah. Okay. All right. Now, a slightly different point of view on how to interpret the circulation. Again, let me just make a geometric, sort of more a physical appeal. Let's suppose that this was like a little leaf, and y'all may recall we talked about little leaves floating in fluids some time ago, right? And this leaf here, well, if I plop this leaf down and the water were flowing as indicated, I submit that we would speculate that the leaf would be rotating, right? And yeah, of course it would. And furthermore, the circulation can be thought of as sort of predicting that. So the fact that this circulation is positive means that the leaf is going to rotate the same direction that the curve is going. Positive means same direction as the curve. Give me 2 seconds. So the curve going counterclockwise, circulation being positive means we expect the leaf also to be going counterclockwise. Yeah.
If the vector field is like tangent to the curve, can you call it a flow line?
But coincidentally, yes. Now, I want to emphasize these, questions of circulation and, it's eventually going to relate to curl, right? But let's not get ahead of ourselves. Are not about flow lines. But yes, in this case, that curve happens to be a flow line, or at least that was my intention as I was drawing it. But again, just a sort of a coincidence. The unfortunate fact that the easiest pictures to understand in terms of circulation also are the pictures that most deceptively suggest flow lines might be related. So that's why I'm making a big deal they aren't. Is that satisfying? Yeah. It's a great question, though. Okay, so let's address this scenario over here, again with the leaf. And now, wait a second, what's up with this? The circulation was negative this time. What's up with that? But the fluid is still going counterclockwise, right? Why is it now negative instead of positive? Well, it's because our curve is oriented, wrong color. Our curve is oriented the other way, right? Circulation isn't as simple as does it rotate clockwise or counterclockwise? It's not like that. Circulation tells you, is the rotation the same direction the curve is going or opposite the direction that the curve is going? And here, with the, I regret that color choice. With the curve going this way and circulation being negative, that's telling us the leaf would rotate opposite of the direction of the curve. And again, well, yeah, right, of course it is. Look at the fluid, right? The fluid's still going counterclockwise, and the leaf is going to do what the fluid tells it to do. Okay. All right. All righty, moving along. We've got some special cases to talk about. These I'm going to go through quickly because I think these are pretty straightforward. Every so often you get lucky with geometry. These are wonderful opportunities. Don't leave money on the table. Don't exert a bunch of effort on some terribly inconvenient calculation when there's a freebie quickie little calculation that'll save you all that trouble, right? And again, years and years of taking physics classes, and y'all have a similar future ahead of you. Stuff like this comes up. It really does. This is not a rare scenario. Huge opportunity for time saver. I don't even know how to quantify it, but it's a very common story. So here's what I mean by fortunate geometry. I have a wacky curve here. Look how wacky, right? I'm giving you the polar position as a function of time. So to get a parameterization, of course you need rectangular position as a function of time. So sines and cosines and such of these already annoying looking expressions, the parameterization's a nightmare. Absolute nightmare. Okay. But very easy to notice that this curve is entirely on the unit sphere. And now geometric appeal, if you're entirely on the unit sphere, then your motion is always parallel to the sphere, right? So this, our dr vector is always going to be a tangent vector to the sphere. Now that's just an observation. Right, okay, next, let me point out that our vector field, where did it go? Here it is, the vector field. Now, weirdo formula for a vector field, but that vector field, you'll notice, is always a scalar multiple of the position. So your position You can think of position as a point, but of course it's also a position vector. And the field vector is always parallel to that, and therefore perpendicular to the sphere. And by the way, we're capitalizing on a unique feature of spheres here, right? The position vector, spheres centered at the origin are the only surfaces that have the feature that the position vector is always perpendicular to the surface. So, fortunate geometry. Right? That's the fortunate geometry. So that said, well, let's get rid of what we don't need. Don't need that. What we have then is, let's see here, that our dr and our f well, it says right here that one's perpendicular to the sphere, one's parallel to the sphere, therefore they're perpendicular to each other, therefore the dot product is 0, and therefore this integral, we're just adding up a bunch of zeros. So the answer is 0, right? No fuss, no fuss. I didn't have to deal with the horrifying nightmare of a parameterization that would have been. I didn't have to then take that horrifying parameterization and plug it into this vector field formula, where that would have made things more horrible, right? Nightmare of a computation. 0, right? Fortunate geometry. Does everybody see how awesome this is? Okay, so be on the lookout. Oh yeah, question.
So, if we're able to deduce that our vector field is perpendicular to the curve,
Yep.
then it's always going to be 0, the line integral.
Yep. Totally awesome. Yeah, good stuff. And again, life, by which I mean life and engineering. I mean, look, certain reality, when you're engineering things, I mean, circles come up a lot. Spheres come up not rarely, right? I mean, we design things in regular ways for, natural reasons. So scenarios where the geometry is convenient are not rare. And so, this, exactly what you said, generalizations of this example are pretty common and pretty sweet to deal with, like so. Good. Okay, moving along. Again, I'm just going to hit the highlights on this. Y'all could pretty much read this. Here's what we've written down. Let me change the color. This is what we've written down previously about dr. That's r prime dt. That's just kind of what I'm going to call vector notation for this fact. And notice nothing really happens when I rewrite that with coordinate notation. That's just coordinates representing r prime. Nothing happened there. And then nothing happened there. I mean, it's scalar multiplying into all the coordinates, well, of course. And then we find ourselves in this situation where it really makes sense to call these coordinates dx, dy, and dz. So, fairly natural to rewrite dr as dx, dy, dz. All right, well, you can write your vector field in coordinates too. Now I've got a dot product in here, right? F dot dr, this dot product turns into a dot product where I got the coordinates. And you could just straight up dot out that dot product. And that would have you write down this. Which, okay, now that's just plugging stuff in. We didn't really hardly do anything there, but what we have is now an alternative notation for a vector line integral. So here's my personal favorite, certainly for Math219 purposes, this is my favorite way to write a vector line integral. It's compact, it's efficient, it's to the point. Everything in terms of vectors. But if you want to write it out in terms of coordinates, you get this. These are what I like to call coordinate line integrals. And by themselves, it's a little bit of a weird thing. Like if you look just at That, by the way, as a for example, integral along a curve of a scalar valued function dx, you'd be forgiven for sort of reflexively thinking, single variable integral, single variable function, everything's a scalar, the integrand is dx. This seems like a Calc 1 thing. And it's not. Right? This is part of an expression that as a whole computes a vector line integral. But you've got to remember that this is not an integral on the x-axis. This is still on a curve in space. There's nothing Calc 1 about this. Right? You got to resist that temptation. What does this look like? What does this represent sort of physically, geometrically? It's hard to come up with a really good answer to that question. And I'll say a couple of things about that. That's why I like this notation. It's because that's a force, that's a displacement, that's work, that's stuff I can point to, draw pictures of, and interpret physically. Satisfying, right? P, what does that mean physically? Well, okay, there's an answer, but it's a bit of a conversation about components and stuff. And what does the dx mean physically? Well, again, you can draw pictures, but it's ultimately fussy and unsatisfying inconvenience for our purposes. So most of the time, we're not going to use this notation, right? This is a kind of, I'm going to say, a liability in the sense that, that notation is going to show up whether we like it or not. This notation is in common use. So you got to know what it is when you see it. You got to know how to deal with it. For whatever it's worth, my take is that when you see this, you should look at these and just remind yourself that that's just a fancy way of saying dr. And then you look at what you might call the scalar integrands and realize that they're just telling you what the vector field is. Use vector line integral you're computing. Okay. Now that said, I do want to recognize this. It's kind of what differential forms looks like. And I think I've talked about that previously. A lot of the big stuff that we're going to be doing in this class, in chapters 6 and 7 that we're just kind of getting into, really is best handled with this construction called differential forms. And the only reason we're not doing the course that way is because it's kind of sophisticated and abstract and bulky and inconvenient, and it's just not worth the trouble. It's a little bit too high level for this class. And for what we're interested in this class, doesn't really buy us anything. The reason differential forms matter is because they are powerful. Bonkers powerful. You can do stuff with differential forms that you can't do with anything else. In fact, historical note. The big theorems that we're about to start talking about, one of which hopefully we'll get to today, we'll see. These big theorems like Green's theorem and Stokes' theorem and Gauss's theorem, fundamental theorem of line integrals. It was known for nearly 100 years that those theorems were true and seemingly somehow related to each other. They have a lot in common and they seem to be kind of analogous, but nobody could really make the connection of how they are really kind of the same. There was this big mystery as to how do these theorems look so similar? And the answer was to think about everything in terms of differential forms. And if you take the differential forms point of view, then all of a sudden, they are literally, those distinct theorems are literally all special cases of the same single unified theorem. They are literally the same thing. And differential forms is the language that makes that possible. So big, weighty, powerful stuff. I am pro differential forms, don't get me wrong. Right? But for Math219, that's all beyond what we're going to realistically do. So I don't expect y'all to actually really get much of anything out of that notation. So heads up though, it is in common use. You are going to see this, And so I think it's important to be able to interpret in the way that we're going to find most useful and convenient when you do see it. All right. Okay, moving along. Symmetry theorems. Again, big fan, as y'all know. Good news. We've got a symmetry theorem for scalar line integrals. For scalar line integrals, there's the theorem. It's exactly what you think. Odd integrand, symmetric domain, integrals equal to 0 by symmetry. Just make sure that you check both conditions, and just make sure that you use the same line for both of the required symmetries. So it's exactly what you would hope. Couldn't be nicer. Nice, clean little package. Cite away. Have fun. Save yourselves loads of trouble. Do be careful. You got to make sure the argument works, right? You do have to be right about it. You know, landmines and all that. But very powerful tool. Now, there's a big asterisk. This is for scalar line integrals only. This does not work for vector line integrals. It does not work, and you can even kind of see why. If you are looking at a vector line integral, right? Remember the whole idea, and let's look at it from this point of view right here. The whole idea of a symmetry argument is that it's sort of equal and opposite on both sides of the reflection line. Just the exact same values, but one's positive and one's negative, and they cancel. Right? Every symmetry argument we've seen sort of rests on that idea. Well, it just doesn't work for the tangent vector there. Those vectors are not the same. And they're also not sort of like conveniently different either. It's not like, oh yeah, they're negatives of each other and that's where the minus sign comes in. No, they're just different. Well, I don't want to overstate it. There is a way to make there's a different take where you can recover a kind of a symmetry theorem. It's more trouble than it's worth. It creates more risk of misapplication than it does save you trouble. So I'm not going to talk about it. But punchline, these aren't the same, and they're not negatives of each other. We lose. Right? As far as odd symmetry goes, odd symmetry does not work for vector line integrals. Everybody see what I'm warning you about there?
I'm sorry, I didn't quite get it.
Yeah. Right, so think back to like when we talked about double integral odd symmetry theorem, right?
Yeah.
And the point is we have a line of reflection, and then you sort of look at a piece over here, and you look at the corresponding piece over here, and they have the same, everything's the same except one's positive and one's negative, right?
Yeah.
So that's the critical point. Everything's the same except for a minus sign. If you do that with this integral here, you look at this part of this curve, you look at this sort of reflected part, is everything in here either the same or exactly the negative between these two sides? And no, the t vector, they're not the same, they're not negatives. So it's just dead in the water. Does that satisfy?
Yeah.
Yeah. So so you just have to be wary about this. It's another landmine that you just got to watch out for. And again, I love this theorem. Used it a million times. Strongly encourage you to use this theorem. Just make extra sure that you remember and retain that it's only for scalar line integrals. Yeah. Okay, so let's do some really weird stuff now. There's different ways to enter into this discussion. A lot of books will start with the fundamental theorem of line integrals. I was a subscriber to that strategy for a long time, and pros and cons, case to be made. Our book starts with Green's theorem, and pros and cons, but let's talk about the pros. There's some really nice advantages to starting with Green's theorem, and I'm going to basically say it is a great, the context of Green's theorem is very good for illustrating a really important general idea. So the next 2 pages of discussion are a general, sort of abstract, general discussion. And we'll apply it specifically to Green's theorem, right after. But this next couple of pages is going to be a foundational concept, an underlying critical sort of roadmap for how we're going to do Green's theorem, fundamental theorem of line integrals, Gauss's divergence theorem, Stokes's curl theorem, and a couple of others depending on how you choose to phrase. And so maybe I'll just leave that aside. But lots of big theorems are all going to follow the same underlying strategy. So that's what I want to talk about here. It's a sequence of observations. So first thing I want to do is define something called a quantity on areas. And it's a pretty straightforward idea. If you give me an area, like some two-dimensional region like this, if you give me some area, I give you some quantity. That's all it is. So for example, let's suppose you have mass distributed across the plane. You give me an area, we could reasonably ask how much mass is in that area. So given an area, there's corresponding quantity. Now here's another one. Area. Forget about mass. If you give me a region, the quantity that I can talk about for that region is, let's say, area. That's another quantity. You give me a region, I can give you an area. Perimeter is another quantity. You give me some region, like so, we can ask what is the corresponding perimeter, right? So I just, when we say a quantity on areas, what I mean is just a sort of a deal. If you give me a region of that, some two-dimensional area region, it's just some number that we associate to that. Okay, and notice it may or may not be physical. This is physical, these aren't. So, think creatively. Okay, next concept. An accumulating quantity is a special kind of a quantity. And the short version of this we've actually talked about previously, but an accumulating quantity I've discussed previously as, just look, I need the whole to be the sum of the parts, right? Chop it up, add it up. And it's a pretty straightforward idea. If I want to talk about how much mass is in that whole, well, physical appeal, but that whole is the sum of the amount of mass on the left and the amount of mass on the right. The whole is the sum of the parts. I mean, that's cool, right? And it's true for mass, and it's true for area. You can think through this right here. If you break it up into pieces, the total area is the sum of the pieces areas. But I just want to note for the record, you can't always assume that everything's going to accumulate, because here's a perfectly reasonable quantity, perimeter, we discussed previously, and it straight up doesn't work. The perimeter of the whole just is not equal to the perimeter of the left plus the perimeter plus the perimeter of the right. In some sense, where you slice it creates more perimeter. Is everybody on board with that? Okay, so I think there's a really huge point. Don't just go, because we are dealing in this class with, there's lots of accumulating quantities, and every integral you ever compute is ultimately of an accumulating quantity. But let's not get too cocky about it. Not everything is an accumulating quantity. So really important observation. You gotta make sure that the quantity you want to apply this idea to actually is an accumulating quantity. The whole does have to be the sum of the parts. And not everything does. Is that cool? Is everybody happy with the okay, we gotta be careful about this. All right. Now this is just a point of view thing. I make the observation that when you have an accumulating quantity, and so I am going to assume now for the rest of this discussion, we're going to be fully focused only on accumulating quantities. Ultimately, accumulating quantities, they behave like stuff. Like mass, something vaguely physical. It's as if every accumulating quantity is physical. Now, let's be clear, not every accumulating quantity is. You could quibble as to whether area is physical. Right? And here's another idea. Work. For example, let's imagine that this area here is the bottom of a pool, right? And somebody's going to have to drain the pool, but somebody's going to have to get down there with a toothbrush and clean all the slime or whatever, right? You got to do, I don't know, they do cleaning periodically. Well, if you've got to get down on the ground in the bottom of the pool with a toothbrush and clean, you can talk about how much total work that's going to take you, whatever units you want to use, I don't care, right? But you can talk about how long that would take as a whole, and if you were to break up the pool into pieces, the whole is the sum of the parts. And the total amount of work is the sum of how much work does it take to do each square inch of that pool. But is work a stuff? Is it physical? Is it concrete? Really? So it's a little bit weird to think of it as being a stuff, but I claim that it behaves like a stuff. Even if it isn't stuff, right? Work, not stuff. But I claim it behaves like stuff in the sense that I can reasonably ask, okay, if work is the quantity I'm interested in, and if I say, look, a grand total, there's a total amount of work distributed over this area, and if somebody asks, okay, how much of that stuff is physically located inside of that little square, I would just say, well, however much work it takes to clean that square, that's how much of this stuff that I'm visualizing it as being is in that square. And it's kind of nonsense. There is no actual physical stuff, but if you were to pretend that there is a physical stuff, no problem. Because the whole is the sum of the parts. This is a feature of physical stuff that we're sort of appropriating for use with any accumulating quantity. Physical stuff has the feature that if you draw a line and you separate, then the whole is the sum of the parts, and we're just saying, well, let's think of all accumulating quantities that way. Is that cool? I know it's a weird ask. This is arguably the weirdest aspect of this whole operation, is this idea that we're going to take non-stuff-like quantities and pretend that they are stuff. Now, again, it's just a point of view. Once you are willing to do that, I'll make the observation that whenever you have stuff, whatever that stuff is, mass, population, number of people, right? That's an accumulating quantity. Work, the amount of work it takes to clean the bottom of the pool, okay? I mean, if you pretend all of this is kind of a stuff, then you can talk about stuff per unit area, and stuff per unit area is a density. Because stuff per unit area, you can multiply by area to get stuff. And we've talked about that on previous occasions. One of the first things we did with accumulating quantities is to say, for example, with mass, if I want to know how to compute mass, how much mass is there in a given little sub-rectangle of a region? Well, mass is mass per unit area. And I'm just pointing out that the fact that mass is literally physical isn't the point here. You could totally make the same kind of sense out of any accumulating quantity at all. Any accumulating quantity. So, again, a little bit weird, but there you go. And, of course, you can probably see where this is going. Once you have a density, you have an integral theorem. So, mass is an accumulating quantity, and mass is mass per unit area times area. Well, same for work. If work is an accumulating quantity, you can think of each little piece of work as being work per unit area times area. And work per unit area I would call work density. We on board? A little strange. But I mean, ultimately, I think a pretty reasonable idea. I mean, imagine yourself again, the pool's drained, you're down in there, hands and knees, toothbrush. You'd probably be sitting there thinking, okay, gosh, every square inch that I do, it's like, it takes me, whatever units of work you prefer. It takes me X amount of effort per square inch as I clean. You're talking about a density stuff per unit size. Yep.
So are we just restating what a double is?
Yeah, in a certain point of view. Yep. That's right. I think there is a very reasonable take that for not overstated, but I can certainly see that in a great many cases, any integral could be thought of as, the integrand could be thought of as stuff per unit area that you're multiplying by area. Absolutely. I mean, it gets weird when you're thinking, like if you're using a double integral over a region to compute a volume, then the integrand is height. If you think about it, maybe it's reasonable to think of height as being volume per unit area. There's a point of view there. Absolutely. So I like that a lot. Yeah. Okay, so that's the game plan, right? This is the game plan. Anytime you have an accumulating quantity, anytime the stuff you're dealing with has the feature that the whole is the sum of the parts, you can think of it as stuff, like it or not. There is an associated density, and you can compute it with an integral. Any accumulating quantity. All right. By the way, I did everything here. Little terminology. Theorems that we end up with like this, I like to call them accumulation theorems because it's all based on the idea that the whole is the sum of the parts, aka that it's an accumulation. So I think accumulation theorem is a reasonable name to call these. Also, likewise, I think it's reasonable to call them density theorems because density is fundamentally the thing that makes it work. I mean, it is the integrand that makes it work. So I use both of these bits of terminology for your consideration. Okay, everything I did there was concerning areas. There is a likewise analogous discussion you can have for volumes. Again, you can talk about stuff that accumulates over volumes instead of areas. Still talk about what it means for the whole to be the sum of the parts, all the same. Everything's the same except three-dimensional, so it's volume instead of area. Likewise, one-dimensional as well. Totally analogous. Okay, all right. Big game plan, right? That's the roadmap. We're going to do some crazy stuff with this big roadmap. Here's our first example. It's going to take place in 2 dimensions. I am going to have to set up a little bit of convention. We're going to have to define what we mean by oriented boundaries, and then we're going to be ready to create a eyebrow-raisingly weird accumulating quantity. But anyway, we've got a little groundwork to settle first. The word boundary, up to now, y'all thought of as just being a curve. That's not going to fly anymore. Now we have to be very careful about boundaries. Boundaries are oriented things. So henceforth, when you see the word boundary, that means oriented in a very specific way. That word is now a loaded word. Boundary means oriented according to a certain convention. Now, what is that convention? Here's the convention. It is totally arbitrary. It's arbitrary but standard. If you're talking about a region, let's say like this. Here's the boundary curve of that region. The orientation on that boundary is the direction that you would go along that boundary, whichever direction you would go along the boundary, that would put the region whose boundary you're talking about on your left. Now, you got to use your imagination here now. So imagine we've got this green region, like, okay, let's say this is like a grassy field, like a nice little meadow or something, and there's a little walking path in blue here, a little walking path going around the meadow. If I walk this way, as indicated, notice the meadow is on my left. If I went the other way, if I went this way, there's nothing on my left. The meadow's on my right. Right? Different. So whichever way you got to go to put the region on your left, that's what we mean by the oriented boundary. Now, I want to address the fact this is arbitrary. Why the left? Why not the right? It seems like somebody's making stuff up, right? We can just make up arbitrary stuff? Yeah, absolutely. We make up arbitrary stuff all the time. And what's important is that when we make up arbitrary stuff, we all have to be on the same arbitrary page, right? Otherwise, everything's opposite. Everything's wrong. Let me point out an example of this that I think y'all will buy into. You know how in physics, electrons have a negative charge and protons have a positive charge? You know why that's true? Because somebody arbitrarily decided it. They made it up. There's nothing intrinsically negative about electron charge. What's intrinsic is that protons and electrons have opposite charges. They're definitely opposites of each other. That much is very clear. But which one you call positive and which one you call negative, who cares? Doesn't matter. Correction. It didn't matter 200 years ago. Somebody made a choice. Some people are not happy with this choice. Right? But somebody made a choice that got set arbitrarily, but it became the standard. And now imagine, this is a silly observation, but just imagine that if you were taking a physics class and you decided, I don't really like my electrons to be negatively charged, I'm going to decide electrons are positively charged. It makes it easier to talk about current and velocity and stuff like that. So I like positively charged electrons. They would laugh you out of the class. Right? Is that right? I mean, so you just can't do that. So anyway, I like to make a big deal out of this because it made me uncomfortable for a long time that this was so arbitrary. But again, we have to make choices so that we can all have a conversation in an efficient way, and ultimately it doesn't matter. So arbitrary, yes, but standard and therefore required. We're going to see several examples of this over the next couple of weeks here. Okay, that's the rule. A misstatement of the rule is that you're always going counterclockwise. Now, it's tempting to say you're always going counterclockwise because you look at the picture and like, well, I mean, come on, look at it. It's clearly, very tempting. But the thing is, not really, because it really only applies while you're going around the outside of the curve. Notice if you take a cookie cutter, right, and you punch out some little holes, like so, that's not counterclockwise, that's clockwise. Everybody see the problem there? So, lots of misstatements about counterclockwise. And yes, that's true if you're going around the outside boundary, and with that in mind, if you want to think of this as a convenient shorthand, okay. Be warned, it doesn't work all the time. Okay, so here we go. We're all ready. It's very exciting. Let me remind you, any accumulating quantity can be thought of as stuff, has a corresponding density, can be computed with an integral. And we are now ready to talk about our first unexpected accumulating quantity. Drum roll. Oh, yeah. Okay.
Sorry, so the magnitude of the boundary is going to be the perimeter of the region, yes?
We've not defined anything called the magnitude of the boundary.
But, well, if I were to add, because it just outlines what the region is, yes?
The word boundary, yeah, pretty much, yeah. But it's just, you talk about the magnitude, I don't know what do you mean by it?
Because if it's oriented, that means it has like direction.
No. The word I hear where you're coming from. The word oriented doesn't mean that you think of the whole thing as a single vector. What it means when we say oriented is that wherever you might happen to look, right, at this point on the boundary, the orientation is that it goes that way. But then at some other point possibly on that same boundary, we're going a different way. It's not that the boundary as a whole is a vector. It's that at every point on the boundary, I need to have some sense of which direction, usually represented by a vector. Yeah. Is that cool?
Yeah.
Yeah. Cool. Okay, so again, accumulating quantities, compute with integrals, powerful stuff. Here's our first example. Boundary circulation. And this seems like a bunch of nonsense. What do you mean boundaries? Boundaries kind of like perimeter. Right? Perimeter does not accumulate. Boundary, like how could this doesn't seem like it's going to work. But it does. It's amazing that it does. But assuming we have some vector field so that we can talk about circulation, I claim the whole of the sum of the parts as follows. Here's the whole. What would be the boundary circulation? Over what curve would I compute the boundary circulation of this whole? Well, the whole has that as its boundary, oriented as indicated there. Now let's talk about the left. Here's the left piece. How would I compute the boundary on that left piece? Well, the boundary circulation. Well, I would have to do an integral on that and then an integral on that. That's the boundaries. That's how I would compute the boundary circulation of the left half. And now let's look at the right half. On this right half, boundary circulation would be, again, following the orientation rules, I would have to do it like that. Again, sort of loosely speaking, counterclockwise. Forgive me for being sloppy. So is green plus blue equal to purple? It sure doesn't look like it. Right? This looks like it appears already to have failed. But what I'm going to do here is so awesome. I'm going to erase the parts of green, blue, and purple that obviously kind of link up. Like if you look over here on the right side, this sort of around the right edge, that part of the blue and that part of the purple, they obviously they're tracking each other perfectly. Likewise, on the far left over here, the green and the purple are tracking each other perfectly. Let's get rid of the stuff that we know matches up and look at what's left. This is our problem. That's our discrepancy. That's the thing that's keeping the accumulation from working. And notice opposite orientations on the same exact curve, which cancel. We're left with nothing. No discrepancy. And boundary circulation accumulates. It's weird. Right? Now, I just want to remind you, let's go back here real quick. We were talking about accumulating quantities, and we talked about how, sometimes things will be physically relatable. We can viscerally, physically think of mass holds the sum of the parts because, oh my gosh, that's how mass works. Right? If this weren't true, if the whole were somehow greater than the sum of the parts, we would all take little bars of gold and keep cutting them into pieces and developing more and more gold, and we'd all be billionaires, right? So this is obviously not going to be. This doesn't make any sense. It's obvious nonsense. But Whether it's something physical, whether it's an actual stuff or not, doesn't really matter. What matters is whether the whole is the sum of the parts, and this has that feature. So this is where the money is made right here. Boundary circulation, weird to think though it is an accumulating quantity.
So instead like partial D1.
Okay, that's just a notation for boundary, sorry. So this symbol, you're right, we use that for partial derivatives, but it's also kind of a convenient notation for boundary. Yeah. Okay, so real quick, I know we're out of time. I hate to leave when we're so close to putting everything together. Give me 30 seconds. Now that we have an accumulating quantity, all I'm going to do is say, well, it's an accumulating quantity, so I can think of it as a kind of a stuff. It has a corresponding density. Turns out we can compute that density, and we'll talk later about all these different sort of notational sort of options, and then you compute it with a theorem. And literally, when you take this stuff called circulation, cite that it is an accumulating quantity, that the whole is the sum of the parts, and that it is computed with a corresponding density, what you get is this bonkers powerful new theorem called Green's theorem that says that boundary circulation is a double integral of curl, just like you suspect, over that interior. So that's where Green's theorem comes from. We'll go through what I hustled through at the very last second here. We'll hit that again tomorrow, and lots more applications. See y'all later. Have a good one.